Okay. Well, it is now
There we-
recording. So, and I can turn on participant screen sharing, which I don't think I'm going to turn it on, but I don't think because I have the files open. So we're looking at number 6.
Okay.
So number 6 has 2 disks.
Mhm.
Those disks are exactly the same.
Yes.
So you're going to pretend those are the same size.
Okay.
Okay, so one's A, one's B, and then we're going to drill a hole in the center of one of them.
Mhm.
So what happens to the inertia?
The inertia increases because more mass is focused away from the center.
You know, that's a pretty good answer because of the way you explained it. But these, right before that hole was drilled, these had the same moment of inertia.
Right. Yes.
Now I took away some mass with a very small r, which means I took away just a little bit of rotational inertia. In fact, you could say that I took away that much.
Right.
So this rotational inertia plus this one is equal to that one.
Right.
This one's less.
Okay.
Now, the difference between them is probably very small because the mass that I removed had a very small r. But, you know, think like, okay, that's 1,000 masses. And this one was 1,000, but then I took out 2 masses, maybe. And those 2 masses had a really small r. So the mr squared, that's I. The mr squared for each little bit of that is very small. But the moment of inertia would go down just a little bit. And the moment of inertia of a disk is a good one to have, is a good one to have memorized also. So the moment of inertia of a disk is 1/2 mr squared, where r is the big radius. Okay. What's the next one after 6?
Number 10.
The moment of inertia of an object about an axis that does not pass through its center. It's always greater. So there's something, I don't know if you've been taught the parallel axis theorem or not.
I believe we have discussed it, yes.
Okay. So, so I'm going to go back to this example that we just were looking at. Let's see here. Okay, so let's say I have a disk and it's spinning like, I don't know if you've ever seen a vinyl record.
Yes, yes,
Okay.
I have.
So that's how it's spinning. And this is the very center of the vinyl record. All right. So that vinyl record has a certain mass m and a certain radius, and I for the vinyl record is 1/2 m r squared. So I know what I is for a flat disc or a tall disc. It doesn't matter as long as it's around the. So I would have that.
Right. Okay.
Now something interesting happens. Let's see. I think I have. I do. So I found a disc. Okay. And so I'm going to make a mark on this disc so you can tell what the disc is doing. So I put a reference mark on there. And now I'm going to take the disc and I'm going to spin it. And that's, you know, this has a certain resistance to being spun because of its mass and radii. And so that's equal to 1/2 mr squared. Okay, now I'm going to scoot this over, oops, so that instead of here, I'm going to pivot it about this point.
Okay.
Okay, so now as I pivot this, so one thing you should notice is that this is the center of mass right here.
Right.
And as this goes around, it's a distance r from the pivot point. Well, I know what I is for that. It's mr squared, because basically it's a point mass, except it's spread out, but it's still, I can treat it like a point mass. Okay, but another thing is happening. As I do this, this is still turning. The disc itself is still turning.
Right.
So not only is the mass going around, oops, I don't know if I, not only is the mass going around this pivot, there we go. So the mass is going around that pivot, but it's also turning as it goes around. So when I move my pivot point out to the edge, so like that, right there, okay, now I have two components of I. I have a component because this mass here is a distance r from my pivot, and I have an I because this disc is still rotating, at least the way that I demonstrated it is. So if that disc is free to rotate, or is not free and has to rotate, I guess is really what's happening, I'm going to have mr squared plus 1/2 mr squared. This one, so this one here is because, oh, the disc is rotating. And this one here is because the mass of the disc is rotating a distance r from P.
Right.
So I always think of this, then the way that I had my students write the formulas, I would call this I subscript O, as in like I original or I about the center. And then this would be I because of the shift.
Okay.
And that's the parallel axis theorem. I about the center, and then I because the mass is shifted. And that goes back to, you know, is it spinning? Is it just spinning about its center, or is it spinning about the edge and the center at the same time? You have both in there.
Right.
So for that reason, if you're spinning something about a different point, if I could drill a hole in this, like right there, okay, well, that's not about the center. So I'd be off to the side. I'd have this whole thing rotating, and I would have the shifted mass rotating. I just need to know whatever that distance is. I should drill a hole in this and I can use this for other people. I'm going to do that. This will be so cool. Not really, but it'll work. Might print a disc. I don't know. We'll see. Okay, so that answers that question about 10. All right, what's next?
Next would be 12.
A constant net torque acts on a merry-go-round from startup until it reaches its operating speed. During this time, the merry-go-round's kinetic energy is, we have choices, constant, increases linearly with angular speed, increases quadratically as the square of the angular speed, or none of the above. So the first thing we know is that we have, it's a constant torque, and that tells me that alpha is going to be constant.
Mm-hmm.
Okay, well in that case, my velocity equation is this.
Right.
And that means that velocity is linear with respect to the acceleration. It's linear.
Mm-hmm.
Okay.
Yes.
But it asked about the kinetic energy. And kinetic energy for something that's rotating is, instead of 1/2 mv squared, it's 1/2 I omega squared.
Right. Okay.
Well, that means that it's going to vary with the square of the angular speed.
Right. And next would be 40.
Okay, so the first thing you have to do is, well, one thing is it's in grams and it's in centimeters. Typically, we report moment of inertia in kilograms and meters squared. It's a kilogram meter squared.
Mm-hmm.
You could express it as gram centimeter squared. It wouldn't be wrong as long as you had the units there. But for me, I would change it to kilograms and meters. Now we have to look and find, it says model the ball as a thin spherical shell. So we have to find the equations for moment of inertia. And, oops. I have to find where that page is.
I think I have the chart here, maybe.
Yes, you do. You should have, it should be in the textbook too. I know what it is. It's 2/3 mr squared.
Okay.
Is that right?
I think it's 2/5 mr squared. Solid sphere about center.
No, but this isn't a solid sphere.
Oh, okay.
This is a thin spherical shell.
Oh, yes. 2/3 mr squared.
And the reason why I thought there was a difference, because I know that the thin one, there's more mass out at the edge. And so that's why it's a higher fractional portion.
Right, okay.
There they are. So it's page 295 in your textbook is where they are.
Okay.
So you might make a note of that.
I will. Yes.
Okay. So we're just going to do 2/3 mr squared. So you know what m is, that's 0.057 kilograms. And what's r?
0.035 meters.
Right. Okay, so that's easy. Next one.
Next one, I think it's right. Next, it should be, yeah, 41.
Okay, so find the moment of inertia about the z-axis. Okay. So basically to find moment of inertia, and you have a set of masses here.
Mm-hmm.
So you have these four masses. The way the masses are drawn, they're really big. So they would have their own inertia, just rotating the mass would. But they said it's four particles. So now we
Right.
have to imagine them as very small. So imagining them as very small, if we want to find I for the whole system, we have to add up all the individual I's. So it's kind of like,
Right.
so now I'm just going to do each individual, the I for each individual one. Let's start with M1. So I for M1 is M1. And then what's the radius from Z, from the Z axis? Or what's the distance?
From the axis. So I'm at like the diagonal length in the square?
Well, M1 is
Or
directly above the Z axis. So M1 is,
right. Okay, yes. Sorry. And three, it's hard to look at that
I
like
know.
that. Okay. Yes. So
So that's,
4.
going to be 2 meters squared.
2 meters squared. Yes. Okay. I see that now.
And then they give us M1, so you can add that value in just a minute. Okay, now let's do M2. So we have M2, and then what's the distance from the z-axis, or the radius for that particle?
M2 is on the z-axis.
So it'd be
So
0. There's no radius.
Mhm.
And then I have M3, and its distance is 2 meters.
Yes.
And then I have M4. What's the length of the diagonal?
So it's a right triangle, so could you just do the square root of 8? Because that's
Exactly. It's the square root
okay.
of 8, which is square root of 2 times either one of the two sides. So it's square root of 2 times 2, which is square root of 8. And so it's going to be the square root of 8, but then that's going to be squared, so you'll get 8 back out of that.
Mhm.
And now you can put in values for M1, M3, and M4.
Yes. Okay.
And M4 was 4. 12 plus 12 plus 32. That would,
56.
yeah. I was a little surprised at how big the I for M4 was, but then I thought about it. It's a little bit more mass, but it's more distance. The R is distance, and
Oh, okay, right.
it's R squared. So square root of 2 squared is 2, so it would be at least double what the others are, and it's times 4 instead of 3. So it caught me a little off guard that it was as big as it was, but that's what we got.
Okay, and next would be 42.
Passes through the center of mass and is parallel with the z-axis. Oh my. Okay, well there's M1, M2, M3, and M4. I put their masses on there.
Okay.
Where's
Yes.
the center of mass of the system?
Directly in the center.
Correct. It's halfway in between the 2 3s and halfway in between the 2 4s. So it's right in the center. And now you should be able to calculate what I is for each one of those. The distance to each mass is just going to be, I mean, it was 2 times the square root of 2 is the diagonal. So it's half of that, just the square root of 2.
Mm-hmm. For each one, right? They would all.
Right. It's going to be the square root of 2 for each one. So then you can just calculate the answer is 28.
Okay. Yeah, 12 plus 16. Okay.
Well, what I realized is each one of them is the square root of 2 away. So it's
Right.
going to be mr squared plus mr squared plus mr. So every one of them is square root of 2 squared. So that's 2. It's 2 times all the masses. So I just added up the mass and doubled it.
Oh.
So that's how I got the answer so fast.
No, yeah, that's even shorter than how I was thinking. Okay. Next one would be 44.
Okay, so now this is an excellent example of the parallel axis theorem.
Okay.
So
right. Yeah.
the first thing, in fact, it's a lot like what I drew a moment ago, except instead of a disk, this is a sphere.
And this time it is a solid sphere.
It is. I think that's 2/5 mr squared.
Yes.
Okay, I have my answer.
Okay. Would it just be the 2/5 mr squared?
Well, you also
Or?
that's about the center,
Right.
but it's also shifted a distance r. So you have to add the shift term. That shift term is whatever the mass is times the distance shifted squared.
MR squared. Okay. Would it be then 7/5 MR squared?
It is.
Okay. Okay. And the next one is 45.
Okay, so we have a 1 meter diameter wagon wheel, and it has a thin rim with a mass of 8 kilograms and 6 spokes, each with a mass of 1.2 kilograms. Okay, so this is a complex shape. So we have the rim. How do we find I for the rim?
I for the rim is 1/2 MR squared.
Nope.
No?
That's I for a disk.
It's
Oh, wait a minute. Let's see. I think I have. Oh, yeah. Oh, yeah. This is. Nope. Nope. That one doesn't work. Where is it? I have a special marker here somewhere. There it is. Okay. So I'm going to take this marker, and so here's my pivot point. And then there's a mass M. Okay.
okay.
Now, if I take this mass M and I spread it out, whoops. This is really hard to do. Okay, if I could do this right, like that, and spread it out, what do I make?
A circle.
I make a thin rim.
Okay.
That's what I make. So I for a point mass is mr squared. I for a thin rim is exactly the same. It's just that the mass is spread out all around the radius, but every bit of mass is the same distance r from the pivot point.
Yes.
Now there is on your diagram, there is one. If you hold up, you have a chart, right?
Yes.
So it is looks like it is the first one, second row. So look at the first one, second row.
The thin-walled cylinder.
Right. If you flatten that out, just like squeeze it together, you get a thin rim.
Oh, okay. Yes.
That's the hardest part about those diagrams is kind of like, Oh, I see how they got a disc out of that or so forth, because the disc is either right next to it or two over. And it actually looks like a can more than a disc. But if you flatten the can, you have a disc.
Mm-hmm. Right.
Okay, so now what is I for the hoop?
I for the hoop is,
MR squared.
yes,
What
which
is
is 32.
M is
8.
8. And what is R?
0.5.
0.5 squared. Okay, so that's going to be 8 divided by 4. That's going to be 2. Yes. Okay, now what about the spokes? What are those?
Are they a thin rod or a point mass?
They're a thin
Or,
rod.
okay.
So
Mm-hmm.
one way to think of it is like this, that
Right.
kind of thin rod.
Mm-hmm.
And right about its center, the I for that is 1/12 ml squared.
Mm-hmm.
Okay, so I could do it that way. I could say 1/12, whatever the mass is for this, and then that's L. Or I could think of it this way, and there's 6 of them. If I do it this way, there's only 3. 1, 2, 3, make 6 spokes.
Right.
But if I do it around the end, then there's 1, 2, 3, 4, 5, 6.
Mm-hmm.
And about the end, it's 1/3 ml squared. That's probably on there also.
Yes. Mm-hmm.
Okay. So that means I is going to be, I like doing it about the end. So that's 1/3 ml squared. There's 6 of them, so I'm just going to multiply that by 6. The mass of a single spoke is 1.2 kilograms. And then L is 0.5 meters
Mm-hmm.
squared.
I got 0.6.
So did I.
Okay. Awesome. And you just add them together, and then that's
That's
it.
it. Yep.
That's it. Awesome.
It's the nice thing about rotational inertia is you are just adding them together. There's no like, oh, it's a vector or anything like that. So the only thing you have to remember is what's your pivot point or pivot axis.
Right.
Is actually makes more sense.
Okay. And the next one is 64.
Okay. So they want the speed of each particle. Ah, I see. Okay. So they're basically having us do this 2 ways, and they want us to see that it really doesn't matter which way you do it. The kinetic energy should come out the same. So if it doesn't, well, that means you made a mistake, or I did. So let's look at the 3 kilogram masses.
Okay.
What is the velocity of each 3 kilogram mass, the linear velocity or speed?
So the formula for that is BT equals 40 meters per second.
Well, they give you numbers in centimeters.
Oh, okay. Take that back. 0.4 meters per second.
Yes.
Okay.
Now, I noticed that you had to look up an equation.
Yes.
You know, I don't know if you remember this equation, but that's how you find arc length. S equals R times theta.
Right.
And that equation, there's another way to remember it.
Over time.
Is this way.
Okay.
That's also arc length, right?
Right.
Circumference is R times theta. That's where the 2 pi comes from. It's actually kind of the other way around. Pi comes from the circumference divided by the diameter. But so C equals R times 2 pi. If I take the derivative with respect to time, which you just mentioned, then I would get this equation.
Right.
Well, that's V equals R omega.
Yep.
That's one you looked up.
Yes.
And if I take the derivative again, then I would get that one. That's A equals R times alpha.
Right.
So all those equations to try to remember, like, oh, how do I change omega to V? That's all. You can just go back to, oh, C equals 2 pi times R.
Right. All the same equation.
It's all the same equation. So as you pointed out, it's 0.2 times 2, so that's 0.4 meters per second. And then we need to do the same thing for the 1 kilogram, which is at 0.4 meters. So 0.4 times 0.2, that's going to be 0.8 meters per second.
Yes.
And that's 1 kilogram. And now we need to do 1/2 mv squared for each one of these.
I got 0.24 and 0.32 joules.
Well, and then you have 2 3-kilogram masses and 2 1-kilogram masses. So if you add up all the kinetic energies, I think you'll get 1.12 joules.
Yes.
Okay, so now we know the kinetic energy, and we did this like translation. We didn't treat it like a rotation problem. We just looked at their, now let's treat it as a rotation problem, which means we do 1/2 I omega squared. Well, they gave us omega, so we just need to figure out what I is. Well, I is going to be, those are point masses, so that's going to be 3 times 0.2 squared. And I have 2 of those. And then 1 times 0.4 squared, and I have 2 of those. And then all of that is times omega squared.
And it's the same. Yep. Okay.
It was supposed to be. So
Yes.
it's good. One thing that tells me is you don't do both of them and add it
Right.
up. You either treat them as if they're rotating or you treat them as if they're linear. Now, these point masses actually are large, so there is a rotational inertia for them, but we're supposed to ignore it. We're supposed to treat these like particles, which it bugs me that they make the particles so big because that's
It's hard to
misleading.
conceptualize.
Just misleading for someone, especially someone who's just starting with this stuff.
And there's 2 left. 65 is the next one.
Oh, okay. So, well, I see 15 centimeters is the diameter. So right away, I'm going to say, okay, the mass, I know that's 1.4 kilograms. And I'm going to change my diameter to a radius. And that radius would be 0.075 meters.
Yes.
I know what I is for a solid sphere. It is 2/5 mr squared. Okay, so that gives me I, and then I have to multiply that, and then 1/2 I omega squared would be the kinetic energy. So 1/2 times I, and then omega squared, well, they gave it to me in revolutions per minute, which is not the standard unit. I need to change it to radians per second. Oops. One revolution is 2 pi, yes. Oh. I had written down that 60 minutes is a second. And I knew that it was supposed to be the 2 pi and the 60 are supposed to be on opposite sides of the fraction. So, so that gives us about 7.5 radians per second, probably something like that.
Let's see. 7.3.
So 7.3 radians per second. And then that's squared. I don't have a guess. I mean, I could guess something.
Oh, 0.085.
Okay.
Okay.
So 0.085 joules, and then they want to add, so that's A, and then B is if we add 5 millijoules, what is the new angular speed. So we just have to, 5 millijoules is 0.005 joules.
Okay. I got 7.6.
Yeah, just go up a little bit.
I have a question. So when you're switching out, like it was in 70 revolutions per minute, how do you keep track of what you're switching it to? Or like to get your desired, because we got it in radian per second.
Well, it's always going to be in radians per second.
Okay.
Omega is measured in radians per second.
Okay.
So when they have it like 70 revolutions per minute, I wouldn't even call it omega. I would call that the RPMs, revolutions per minute. So, but it's just dimensional analysis.
Right.
The units, so if you kind of think about the mr squared and then multiply that by omega, that r is meters per radius, and that omega is radians per second. So in order for them to combine to give you meters per second, the same thing you'd have with 1/2 mv squared, it's got to be in radians per second.
No, that makes sense. Okay. And the last one, if we have time, is 69. Because we're already past the 50.
That's all right. Okay, uniform. Oh, boy, that diagram's really awkward to look at too. That thing labeled axis is coming out of the page at us.
Oh.
So it's released with the, so if this is the ring, it's released like this. I guess it'd be like this. So it's released like this, and then it's going to swing down.
Okay, yes.
And it wants to know what is the velocity down here at the bottom. Okay, so up here I have a certain potential energy, and then that's all going to change to kinetic.
Yes.
Well, if I'm looking at that as my starting condition for my potential energy, the height is r, which is half the diameter. So I'm going to write before, and then my potential energy is the mass times g
times the height of 0.75. Okay.
Right, but I'm just going to write d over 2. Actually, I'm just going to write r because that's what the change is, and then you know what r is going to be. You can plug those in. So, and then the kinetic energy at the beginning is 0.
Right.
Okay, now the after condition is the potential energy is 0, and my kinetic energy is going to be 1/2 I omega squared. Okay, so I for that hoop is not just mr squared, because it's not just pivoting about its center, it's pivoting about the edge. So this is mr squared, and then I shift it a distance r. I shift m a distance r, so that's going to be, I is going to be mr squared plus mr squared. one mr squared is about the center, and the other mr squared is because of the shift.
Right.
So basically, these two things have to be the same. My MGR here. And then my 1/2 mr squared plus mr squared.
Right.
One-half I. That makes sense.
Okay.
Okay, and you can just plug in the numbers. You've got that.
Yes.
All right, I shall stop recording.